Assalamualaikum warahmatullahi wabarakatuh, and hi. So today we will proceed to chapter 3, which is entitled Properties of Pure Substance. Okay, so first of all we look into their object. Okay, the objective for this topic first is to introduce the concept of a pure substance. Second, to discuss the physics of phase change processes. Third, to illustrate the PV, TV and VT property diagrams and PVT surfaces of pure substance. Fourth is to demonstrate the procedure for determining thermodynamic properties of pure substance from table of property data. Fifth is to describe the hypothetical substance, ideal gas and the ideal gas equation of state. Sixth is to apply the ideal gas equation of state in the solution of typical problem. 7. To introduce the compressibility factor, which accounts for the deviation of real gases from ideal gas behavior. And the last one is to present some of the best known equation of state. Okay, first we look into pure substance. So what is pure substance? Okay, pure substance is a substance that has a fixed chemical composition throughout. For example, water, nitrogen, helium and carbon dioxide. So air is a mixture of several gases, but it is also considered to be a pure substance since it has a uniform chemical composition. Mixture of oil and water is not a pure substance since oil is not soluble in water. Okay, for example, we can imagine or we already know when we mix oil and water, so oil and water cannot mix together. So oil and water is not a pure substance. A mixture of two or more phases of pure substance is a pure substance as long as the chemical composition is the same. For example, the mixture of ice and liquid water. Okay, for example, in this figure, a mixture of liquid and gaseous water is a pure substance, but a mixture of liquid and gaseous air is not. So meaning that vapor plus liquid is a pure substance, but vapor, liquid, gases is not a mixture. Nitrogen and gaseous air are also a pure substance. So pure substance does not have to be of single chemical element or compound as long as the mixture is homogeneous. So phases of a pure substance. Okay, to identify it as having distinct molecular arrangement that is homogeneous throughout. At room temperature and pressure, copper is a solid, mercury is a liquid, and nitrogen is a gas. So these three principal phase is a solid, liquid and gas. So this is state of matter. Okay, the arrangement of atom in different phases. So we look into A. This is the general arrangement for the solid, and for B is the general arrangement of atom for the liquid, and C is the general arrangement of the gaseous phase. So phase change processes of pure substance. Okay, first we have a compressed liquid, also we call as a subcooled liquid. So what's the meaning of compressed liquid? So compressed liquid is a substance that is not about to vaporize. So meaning that it's still in liquid situation. So what is saturated liquid? Saturated liquid is a liquid that is about to vaporize. For example, state 1. So we have this. So state 1, we have the pressure equivalent to 1 atmosphere and the temperature is equivalent to 20 degrees Celsius, and then we apply a heat. So this piston, as temperature increase, liquid water expands slightly and so its specific volume increase. So piston will move slightly, pressure remain 1 atmosphere since the process depend on the outside barometer pressure, and weight of piston which both are constant. So water still a compressed liquid at this stage. So at state 1, normally water is still a compressed liquid. So we can simplify it at 1 atmosphere and at temperature 20 degrees Celsius, water exists in the liquid phase compressed. Okay, at state 2, so more heat being transferred into the piston will increase the temperature. So any heat addition will cause the liquid is to vaporize. Phase change from liquid to vapor about to take place. So meaning that in state 2, we have the pressure equivalent to 1 atmosphere. The temperature is increased from 20 degrees Celsius into 100 degrees Celsius. So at 1 atmosphere pressure and 100 degrees Celsius, water exists as a liquid that is ready to vaporize, where we call as a saturated liquid. Saturated vapor. Saturated vapor is a vapor that is about to condense. Okay, so when we refer to this figure at state 3, so we have the pressure equivalent to 1 atmosphere, the T equivalent to 100 degrees Celsius. So as more heat is transferred, part of the saturated liquid vaporize, which means saturated liquid vapor mixture, since the liquid and vapor phase coexist in equilibrium at this state. Okay, so this is the state 3 is a situation where the saturated liquid vapor occur together. Okay, and then state 4, so state 4 is a saturated vapor where a vapor is about to condense, where the pressure is equivalent to 1 atmosphere, the temperature also constant at 100 degrees Celsius. So at 1 atmosphere pressure, the temperature remains constant at 100 degrees Celsius until the last drop of liquid is vaporized, where it means at 100% saturated vapor. So heat loss will result vapor to condense, where vapor start condense to liquid. So the vapor resulting in the condensation process. State 5 is a superheated vapor. So what the meaning of superheated vapor is a vapor that is not about to condense. Okay, saturated vapor is a vapor that about to condense. But the superheated vapor, the vapor is not about to condense. Meaning that this state is not a saturated vapor. So for example in state 5, so the pressure is 1 atm and the temperature is increased to 300 degrees Celsius. So as more heat is transferred, the temperature of the vapor start to rise, where it becomes superheated vapor. Okay, when we look into the entire process between state 1 and 5, so we can describe in this figure where state 1 and 5 we describe in the figure is reversed by cooling the water while maintaining the pressure at the same value. So the water will go back to state 1, okay, retracing the same path, and in so doing, the amount of heat released will exactly match the amount of heat added during the heating process. Okay, so this is a TV diagram for the heating process of water at constant pressure. So we can see from what we learned before for the saturated vapor, superheated vapor, saturated liquid vapor mixture, compressed liquid, and saturated liquid. So all state is occur in this TV diagram. So we have a state 1 where is a compressed liquid, state 2 is a saturated liquid, and state 3 saturated mixture where the existing between liquid and vapor. State 4 is a saturated vapor, and state 5 is a superheated vapor. Okay, so what is saturation temperature and saturation pressure? So saturation temperature, where we call as a Tsat, saturation temperature, the temperature at which a pure substance change phase at a given pressure. So meaning that Tsat is, we have a given pressure, let's say when we refer to table 3.1, the pressure equivalent to 3.17 kilopascal. So the Tsat is 25 degrees Celsius. So that is what we call as a saturation temperature. So same the meaning for the saturation pressure. So saturation pressure is the pressure at which a pure substance change phase at a given temperature. So when we're referring back to the table 3.1, we can say that at temperature equivalent to 100 degrees Celsius, the P set is equivalent to 101.4 kilo Pascal. So this is the T set and also the P set. So meaning that temperature at which water start boiling depends on the pressure, and therefore if the pressure is fixed, so also is the boiling temperature. Okay, latent heat. So latent heat is the amount of energy absorbed or released during a phase change process. Okay, and then the latent heat of fusion is the amount of energy absorbed during melting. So it is equivalent to the amount of energy released during freezing. And latent heat of vaporization is the amount of energy absorbed during vaporization, and it's equivalent to the energy released during condensation. Okay, the main important thing for what we need to understand by the latent heat is the amount of energy absorbed or released during a phase change process. Okay, so this is you need to understand. So latent heat is the amount of energy that you use when you absorb or you release during the phase change process. So same for the latent heat of fusion. So you already understand for the meaning of latent heat. So during a fusion is the energy absorbed during melting. Okay, so the amount of energy that you absorb during the melting, or it also equivalent to the amount of energy that you release during freezing. Okay, so same goes to the latent heat of vaporization. So vaporization is the amount of energy absorbed during vaporization, and also it is equivalent to energy release during condensation. So you need to understand the definition and also the understanding of the latent heat of fission, and also the latent heat of vaporization. Okay, after all, from today's lesson, so you need to understand for the phase changes and the various of state occur, and also what's the meaning of latent heat of fusion, and latent heat of vaporization. Okay, so and then we will continue in the next topic regarding to the variation of the standard atmospheric pressure and the boiling saturation, and also how to calculate the variation of energy absorbed and energy released during the state process. Okay, after all, thank you very much for listening.